Hello everybody. I would like to welcome you at the session about forecast evaluation. Can you hear me?
Yeah.
Great. Today we will have three speakers. Let me put my video on. Okay. Today we will have three speakers. So one of them is not still yet there, but hopefully he will come in a couple of minutes. So two distinguished speakers and me. So each of them will have 20 minutes, and I will provide a gentle reminder before the time will run up. He just wrote me he's coming, so everything is fine. All three presentations will take place. So okay, so I will share my screen and let's get started. Today I would like to talk, so let me introduce myself. I'm Filip Staniek, I'm a PhD student from CERGI. And today I would like to talk about forecast evaluation, auto-sample forecast evaluation, or some people call it time series cross-validation, depending on whether you come from econometrics or machine learning background. And in particular, I would like to talk about how can we do it better than we are currently doing. So let me start with the diagram. This is what people usually are doing. So we have some segment of the time series of length t. And what we usually do, we estimate the model or train the algorithm, depending on where you come from, train the model of some subsegment of that time series of length m, and then we make forecast for v consecutive periods. And for each of these out-of-sample periods, we record how well using some contrast function, we record how well the forecast were. So the contrast function is usually squared error, but it need not to be the case. And then what we do, we move the window again, and we do that until we arrive at the end of the sample. And finally, we just take average of the auto-sample contrast. And that's the loss estimator. So this is what you usually are doing. Now, what's our contribution? We propose an alternative estimator using exactly the same scheme, but utilizing the information differently. So we propose this LACV estimator. We call it A because it augments the information from the auto sample with the information from the in sample. So we combine both in some optimal manner. And the CV stands for cross-validation, obviously. And this is the main result of the paper. Provided that the series is stationary, we prove that the proposed optimal estimator is of same expectation. So it retains unbiasedness for the object which we are trying to estimate. But more importantly, we prove that it always has lower or at maximum equal variance than the regular estimator. So it dominates the regular estimator. So why that is interesting? Well, sometimes you just want to estimate the loss, and having more precise estimator of the loss, that's neat in itself. But sometimes we might want to do something more intricate. So for example, we might have two algorithms and we want to test whether the observed difference which we see is significant. So we have some benchmark and then we propose some alternative and we want to test whether it's significantly better or worse. So that would be the Diebold-Mariano test or Ibragimov-Ed Miller test or Giacomini and White test, for example. And what we show that in these tests, if you instead use the optimal estimator, you achieve much higher power in detecting the null hypothesis. So you will get more powerful testing. And second application is sometimes you use the cross-validation as a matter of selecting new models. So you have multiple models and you're unsure which one of them to use in the real out-of-sample forecasting. And what you usually do, you do the cross-validation for each of them, estimate their losses, and then select the one with the lowest loss. And what we demonstrate that if in this exercise you are using the more optimal, the optimal estimator LACV instead, then you are less likely to select bad model by accident, and consequently you will have better forecasting performance. So let me show you.
Can I ask you a question?
Yes.
So when you have this expression number 1 here, when you have the LCV and LACV, these are loss measured, right? Yeah, but they don't have hats on them. So my question is, are you assuming that these properties that you prove are based on population estimates? Imagine that we're generating the models with the estimated parameters in a regression framework. So these results are obtained with estimated parameters or population parameters.
Yes, sorry, I should highlight the notation. So I have quite, so in my notation, we denote the estimator by normal L, and then we denote the object, its expectation by this calligraphy L. So it's instead, yes, so we don't use hat because that would be, the notation is already quite complicated. So we decided to do it like this. So this is, in fact, this is estimator, not its expectation.
Okay. So it contains, it's the loss function that I would obtain in a usual auto-sample exercises with estimated parameters.
Yeah, this would normally be written with head, but we just omit the head for simplicity in the notation and use the calligraphy L instead. Mm-hmm. So yeah, sorry for the confusion. Yeah. Okay, so let me actually show you how it works. So this would be the diagram for the proposed LACV estimator. And here you can see that we are not only using the out-of-sample contrast, but we are using all the in-sample contrast. And obviously we just cannot average them because that would be apples and oranges, but we still can use somewhat them to improve the precision of the estimator. So let me start with the notation. So this would be the empirical contrast. So that will be, again, without the head, but yeah, this is a sample measure. So that would be denoted by L, and the first upper index is length of the estimation window. So in this case, that would be 17. The second upper index is the shifting index. So that tells us what's the position of the window with respect to the original window size. And then most importantly, we have the lower index, and that's the position of the contrast within that window. So if the lower index is less or equal than the first upper index, that means that we are talking about in-sample contrast. If the upper index is smaller, that means that we are talking about the out-of-sample contrast. So this is the notation. And finally, we can express the classical loss estimator, which is just sample average of these contrast, out-of-sample contrast. That's why we have M plus J here. And as a matter of convenience, we will define this calligraphy LCV to be its expectation. So that's the object which we are trying to estimate. Okay, so continuing with the notation, what we do, we define phi to be a vector in which we stack all the in-sample and out-of-sample contrast into one very long vector. So everything is in there. And then we will be considering estimator of this form. So we have vector of all the in-sample and out-of-sample contrasts, and we have some weighting. And the strategy which we'll be pursuing is we will first select a set of admissible weights such that no matter which weight you choose from that set, it will retain unbiasedness. And second, we will find weight in that set which minimizes the variance. So again, let's be more precise about that. In the paper, we proved that provided that these two conditions are satisfied, so the first condition tells us that, so this would define the set of admissible weight. The first condition tells us that sum of weights for the in-sample contrasts, so this would be the position, that's in-sample position. So sum of weights for the in-sample contrast across the different shifting indices must be equal to 0. So they must cancel out in expectation. And the second condition is that sum of weights for the out-of-sample contrast across the different shifting indices must be equal to v to the power of -1. So they do not cancel out in expectation. So this defines the set of admissible weight which deliver unbiased estimator. And then because these are linear restrictions, we can write it in a matrix form as some b times lambda equal to b. And then the optimal variance minimizing weight is given by this formula. Here, the v phi is the covariance matrix of the phi vector. And well, this is the optimal weights. And in practice, however, we don't know the V5. So we have to estimate it. And in the paper, we propose estimator for that, but usually the time is rough here. So I am not sure whether I will be able to describe it in detail, but we can estimate it somehow, the V5. Okay, so this is the formula for the optimal weight. So let me actually show you the intuition behind it, because it's the idea is actually quite trivial, but it works well in practice. So this is the weights which would correspond to the regular loss estimator, LCV. So you can see, so the color as well as the number, that's the value of the particle weight. And you can see that for the regular estimator, we place 0 weight on all the in-sample contrasts. So these are all 0. And then we have 5 auto-sample contrast, and this is fixed scheme. So V equal N equal 5. And because we have 5 of them, so each of them is given weight 0.2. So that would be the standard estimator to use this kind of weighting. Now, this is what we actually propose. This is the optimal thing to do. So again, you can see that for the auto-sample contrast, they still get the same weight. They get weight 0.2. But on the right-hand side, you can see that there are some negative weights, slightly, gradually diminishing as we move back to the sample, and the same on the left-hand side, except that it's positive. And let me demonstrate why this is the case. So imagine that there will be some huge idiosyncratic shock in the period 50. So that would mean that this contrast will be likely much higher, because we are not good at predicting that particular period. But that also means probably that the in-sample contrast from that same period will also be unusually high. So these are correlated. And what you might think, well, if these are correlated, then, and we include one of them with positive weight, we might include the second one with negative weight to somehow counteract the idiosyncratic noise from that period, because that would at least partially cancel out each other. And indeed, you can do that. But remember, we have to retain unbiasedness. So the weights for each in-sample period across the different shifting indices must be equal to 0. So we have kind of this is equivalent period ex ante. So we have to include them with exactly the opposite weights, such that they ex ante cancel out. So if we include this with negative weights, we have to include this with positive weights. And then you can notice that we just move the problem kind of one step up. So we can repeat the process again. These are highly correlated among each other. From kind of the rows are highly correlated. So again, we include this with some negative weight to eliminate part of the variance. And then we use this with this exactly opposite positive weights to eliminate the introduced bias. So, and we do this until we arrive at the end of the sample. So it's a very simple idea, but as you will see, it works very well. The variance reduction is quite substantial. So we can do the same for the rolling window. Again, you can see that on the right-hand side, you have negative weights, which help to eliminate the idiosyncratic noise. And on the left-hand side, you have positive weights, which eliminate the introduced bias. But the idea behind that is exactly the same. Okay, so let me show you how well it actually performs. So this is, in this figure, you have, on the x-axis, you have number of in-sample observations. On the y-axis, you have number of out-of-sample observations. And the color, as well as the first number, is the ratio of the variances. So, and these diagonal lines, these are common in-sample, out-of-sample splitting rules. So some researchers, for example, tend to choose that they left 1/3 of the sample for the out-of-sample evaluation. So that would be this line. And along this line, you can see that the ratio of the variances is below 0.5. So that means that we reduces the variance by factor of 2, which is I believe, not that bad. But if you look at the different sample splitting rules which left less observation for the auto-sample evaluation, here the benefit is even stronger. If you look at the rule 1/10, for example, you can see that we reduce the variance by factor of 10. So that's quite good. Okay, so
Philippe,
that would be,
Philippe again. So I'm kind of lost with. So I was thinking. Imagine that we have a square loss So you have the in one extreme, you have the in-sample evaluation of your loss function. Let's say it's like the sum of square residuals or the average of the square residuals. On the other hand, if you're estimating a square loss, again, you can have like something similar but without a sample. So I was thinking that probably the in-sample measure of this loss function would underestimate the loss function, would have a bias, downward bias. The auto-sample would have an upward bias. I'm not thinking about variance of the estimates. I'm thinking about bias in the estimates itself. And I would imagine that your approach would be like in between. But I'm not sure which one is more, I guess, I don't know if you provide simulations in which your estimate is more accurate in terms of point estimates of the true, let's say, sigma square of the models. And I'm come from econometrics, so I'm not sure if you have the same background. But I don't know, do you understand what I'm saying?
No, the important thing which I would like to stress is that the expectation of the proposed estimator is exactly the same as the original estimator. We don't introduce any bias at all. That's we know that the in-sample contrast, they are kind of systematically smaller because there's overfitting going on. But that's the reason why we include them in a very specific way. You can see that they ex ante cancel each other. So they don't introduce any bias ex ante. And so that means that the estimator is still unbiased, but it's of lower variance because we were capable of leveraging the correlation between the in-sample and out-of-sample contrast.
So, but the gains of your approach are measured in terms of variance then? So is the variance is much lower in your approach than in traditional approaches?
Yeah, that's the case. That's essentially all we are claiming. We are claiming this is what people are usually doing. You can do this, you will have the same expectation, much lower variance. That seems like a good deal.
Okay.
Okay, so what we do further, so this is kind of the raw estimator. We have some applications. One of them is testing for forecastability. So we have a null hypothesis that we have two algorithms, and their one ahead loss is the same. So that's the null hypothesis. The typical way to approach this would be with the Giacomin and White test or Diabot-Mariano, depending on which framework you want to consider. And we provide alternative tests which utilizes the optimal estimator, and it correspondingly adjusts the variance. And recently in Zuckerman, they proposed to use Ibragimov and Miller subsampling procedure to kind of avoid the need of estimating long-run variance. And again, we propose an alternative test which utilizes the optimal weighting instead of the regular weighting. And then we have some simulation exercise adapted from Giacomin and White. And here, this allows us to simulate we define tau as the ratio of the losses. So if tau is equal to 1, the null hypothesis is satisfied. If it's not, then it's violated. And here you can see the power of these tests. So the blue line is the proposed augmented test with the information from the in-sample, and the red line is the regular test. And you can see that under the null, they both reject approximately with 5% frequency. It's not really that visible. I have tables in the paper, but approximately at 0.005 frequency. But as we deviate from the null hypothesis, the proposed test is much quicker in detecting the deviation from the null. So these tests, which utilizes the optimal estimator, are more powerful than the standard estimator. And the difference is especially substantial for the Ibragimov-Miller test, which is generally not that powerful on its own. And then we also do exercise for algorithm selection, but unfortunately, I don't have time to go through that in detail. So just in conclusion, we have this new estimator, which delivers substantially smaller variance. And when applied to the testing, it delivers much higher power. And okay. And so here you can download the article, and we already program R package, which do the estimation for you. So if you want to try it out, you can go to the GitHub or you can directly install it in R. So thank you for attention. We can discuss it even after the session. The session does not have to end at 0.00. Okay. So I would like to pass the word to Dr. Pablo Pinchera, which we will be talking about correlation test of predictability. Thank you for attention.
Okay, so can I? Yes. I don't know if I can share.
Yeah.
Let me see.
It should be possible now.
Should be possible now. Let me see. Let me see if I share screen here. Here it is. Okay, so you should be able now to see my presentation. So hello everybody, I'm Pablo Pinchero from Chile. So here is 6 a.m. in the morning. So just slept like a couple of hours. So this is joint work with Nicolas Hardy. Nico who's here. Where are you, Nico? I cannot see you while you're here.
Yeah, I'm not with the camera, but I'm here. Yes, thank you.
Okay, so here you are. So this is a correlation-based test of predictability. So what do we do in this paper is that we show that, first of all, we notice that the traditional mean square prediction error comparison between models are highly controversial. This is because we detect a paradox with mean square prediction errors, which is something that is probably usual to have in empirical applications. So we detect this paradox, and we detect the paradox zone that is not an empty set. So let me explain what happens here with the paradox. You know that mean square prediction error is a quite standard measure of predictability. Actually, it is used here. Nico was able to find the word mean square prediction error mentioned 70 times in West 2006 forecast evaluation survey, and it's been used in a huge amount in a number of papers in the literature. So it's quite an important measure. However, what we realize is that something that we show with the simple decomposition is that whenever you're comparing two forecasts, it might be the case that the forecast displaying the lowest mean square prediction error is also displaying the lowest correlation with the target variable. So that's the paradox. So you would expect that a good forecast in terms of mean square prediction errors is a forecast that has low mean square prediction error, and a good forecast in terms of correlation with the target variable, with the variable that you're predicting, is a forecast that has high correlation. And you would expect to have a connection that these two measures, mean square prediction error and correlation, to be connected in such a way that the optimal forecast in one measure is the optimal forecast in another measure. Well, that doesn't happen all the time. So so here we have a simple illustration. Imagine that in our world, we just realized we're just working with stationarity. Everything will be fine. It's a standard time series setup. So imagine that we have, to illustrate the paradox. Imagine that we're forecasting YT. So for this example, we're making a lot of simplifying assumptions that will be removed in the rest of the paper, are removed in the rest of the paper. It's just to give you an illustration. So imagine that we're predicting a mean zero target variable with variance equal 1. We have at time t, we have two competing forecasts, xt minus 1 and ct minus 1. These are forecasts for YT. We will drop the sub-indices just for simplicity of notation. They are all weakly stationary. So mean square prediction error of when predicting with the forecast x is given by the expression here, the expected value of y minus x to square, and the same expression when we're forecasting with forecast z for y. So we define here the mean square forecasts, which is the expected value of the square of the forecast, And now imagine that we're interested in comparison of mean square patient error. So the difference in mean square patient error is given by the mean square patient error of the forecast X minus the mean square patient error of the forecast Z. So here's the difference. And it is very simple to show that the difference in this mean square patient error satisfy this expression here. So we have that, this is just algebraic manipulations to show that a connection between the difference in mean square patient error and the difference in correlations between the target variable and the forecast. So what we have in this very simple setup is that the difference in mean square patient error depends on this difference of mean square forecast minus 2 times here a positive term times the correlation of the stuff. Imagine that in a perfect world, what we would expect is something like where this term here is 0. If this term here was zero, what we have is that a perfect world in which the forecast with the lowest mean square patient error, let's say X, is equivalent a forecast with the highest correlation relative to Z. So if this is negative, this will be positive here, right? So there will be perfect syntony or a connection between the both measures. But this term here destroys this relationship and induces a paradox. So if this term here is positive, then we might end up having the paradox in the sense that, for instance, forecast X has low or the lowest mean square patient error relative to Z, but it has also lowest correlation with the target variable, which is something very, very bad. And this is very relevant for the econometrics literature, because in the simplest case in which one of the forecasts is the zero forecast coming from the random walk without drift or with drift. Remember that if we have a drift, in this case, we're considering the simplest case of a random walk without drift. So the forecast for the variable Y is exactly 0. So then the covariance between Y and Z will be 0, and the mean square forecast Z will be 0. And we assume, just for simplicity, that X is an unbiased forecast and that variance of Y equals 1. We have the paradox here because the difference in mean square patient error is, or the paradox is generated by this term here. So there's no connection between the correlation of the variable of the forecast with the target variable and the mean square patient error. You know, the mean square patient error of the forecast that is 0 and has 0 covariance with the forecast can outperform a forecast, a more useful forecast in terms of correlation that will have something to say that will be associated to the forecast to the target variable Y. So that's the source of the paradox. And here we have a more general framework in which we relax the simplifying assumptions of variance of Y equal 1 or unbiased forecast, whatever. This is quite general, so we have a more complex expression here, but we are also able to get some propositions here. So in the case of the zero forecast, then we'll find a paradox as long as the covariance between the forecast, for instance, if we're comparing the zero forecast with a non-zero forecast, that in this case is denoted by X. So we'll have the paradox as long as the correlation between X and the target variable is relatively low. So it relies or lies in this interval 0 and this upper bound here given by the square of variance of Y of X over the square of variance of Y over 2. Notice, for those related to econometrics, this is something that is similar to to the R square. So the coefficient of determination. The coefficient of determination should be given by the variance of Y, the variance of X over the variance of Y. So this is a square root of the coefficient of determination. So this is implicitly saying that this paradox can only hold true when you have inefficient forecast. So in a world of efficient forecast, you won't have the paradox. But so we have more regions for the paradox, and I had some charts here that I don't have time to show you because we have we're running out of time here. But here some charts depicting the paradox. But what we show is that this is proposition 4. If X and Z both forecasts are efficient at Mincer and Sarnowit, then it is not possible to find the paradox. But of course, what happens in the literature is that when you read empirical literature or build out a sample forecast, it is quite often the case that you find inefficient forecasts. They have bias, small biases, and this is not only happening when you analyze surveys. There's a paper by Inge and Molotova for exchange rate literature that is picking different surveys, and they show that the forecasts generated by the surveys are biased. The same happened with the survey in Chile for inflation, exchange rates, and many other variables. And some institutional forecasts we have analyzed, for instance, Central Bank of Chile's forecast for GDP growth and inflation, and they tend to be optimistic in terms of GDP growth. So finding inefficient forecasts on Mincer and Sarnowit is something quite often, even if you're modeling this stuff. Even if you're modeling, if you're running a regression, a simple regression, you find that your in-sample forecast should be efficient at Mincer and Sarnowit, but then out-of-sample forecasts and out-of-sample errors tend to show some degrees of inefficiency. So this is quite often. So we think that the paradox is something that should happen. So based on this paradox, saying, well, if we sometimes we would like to have a forecast with the minimum square prediction with mean square prediction error, but sometimes we would like to have a forecast with the highest correlation with the target variable, which is quite intuitive, because it can give you information about what's going to happen with the target variable in the future. So we would like to tell apart two different forecasts in terms of correlation within a test for that. So we propose a test based on the, so here it is. We propose a test, well, this is just based on the delta method. We apply the multivariate delta method twice to this vector of sampling moments of the forecast X, Z, the target variable Y, the squares of this, the mean square forecast here, and the covariance of the cross terms of these stuff, the expected value of X times Y and Z times Y. And we apply the central limit theorem, and with the delta method, we're able to build a very simple test that is comparing correlations between the forecast and the target variable, or two forecasts and the target variable. So here we have, this is the sampling standard error of the target variable. This is T, this total sample size that we're considering. These are the sampling correlations, should be rho X. Well, rho is meaning here population correlation. So sampling correlation between X and the target variable Y, sample correlation between the forecast Z and the target variable Y. And here we have, of course, a standard deviation that is quite complex object, and is given by this expression here. Well, this is sandwich expression where this nabla G terms here depends. It comes from the delta method. It depends on expected values of the forecast and of the target variable that, of course, we need to estimate with sampling mean with sample means. And here we have the long run variance that is given by this expression here. Is horrible expression. So if you want to use this, you will have to ask Nico for the code or to compute all this term. But this is not that horrible, because it just applied in a standard software. You just say, this is the vector of whatever thing that we have a lot of terms here, Y's, X, and Z, and you just compute the long-term variance of this stuff, and it's provided by New West or Andrews, something quite automatically. So there's a friendly user version of our test in which we assume that these terms here are zero. Imagine if these terms here are zero, this nabla G term. So this simplifies quite a lot. So this not go to zero because we have these ones here. So, but the computation of this variance is much more simple. And here you have the expression is nabla h times this. Now the longer variance of these terms is given by here. So we have a friendly user version of our test that is simpler, and the full version, the heavy-duty version of our test, and we'll show you how it behaves in Monte Carlo simulations. Here, I don't know where we're in time. So here we have a data generating process inspiring Bussetti and Marcucci, 2013, published in the International Journal of Forecasting. So it's a simpler VAR1 for the variable y. And here we're assuming we're inspired by the literature saying, okay, imagine that y is some sort of inflation measure. It has some persistency here. And there's another variable that predicts inflation, but this variable is unobservable. So imagine that we have, so there's some question here. 5 minutes remaining. Thank you, Philip. So imagine that we have two ways to approximate this unobservable variable x. So we have one way z, or another way c1, c2. This is, for instance, inspired in different ways to approach GDP gap, something like that. So you don't know what is a potential GDP. So you have two different approaches to approximate true potential, the output gap or something like that. If you're a macroeconometrician, for instance. So we build two competing forecasts based on this AR1 thing and these two different measures for the unobservable variable x. So we need to play with all these parameters here, betas, alphas, and the shocks, and the variance of the shocks, in order to impose a null, because we would like to impose a null in which correlation between the two forecasts, y1 and yt, is equal to the correlation between y2 and yt. So for that, we need to play and set our parameters correctly. So we impose the null hypothesis for three different scenarios: low, medium, and high correlations, to see how our test behaves. So we play with the parameters, and we consider different sample sizes. And this is of course we use New West. No, not of course, it is one of the alternative. And here are the results in terms of size. So we have the low correlation results scenarios at a nominal size of 10% and 5%, mid correlation scenarios, nominal size 10%, 5%, the same thing for high correlation, different sample sizes, 2,500, 150 observations. We have the results for the correlation full, the heavy duty correlation test, and our friendly user version, in which we demean our series to mimic the situation in which the series have zero mean. And we see here that the test behaves quite well in large samples, and we have some distortions here where the sample size is small, just 50 observations, but that doesn't happen for the full test, for the heavy-duty test with all the terms involved. It just happened for our friendly user version of the test. Here you can see that the test is the distribution of the test is normal. We also try with simulation with non-normal distribution, with heavy tail shocks, and we have some size distortions when we play with very small number of observations, 50 in this case. We have a large sample size of 2,000 observations. Both versions of the test behave very well. So here there's room for improvement. So for another paper which introduces a sample size adjustment for our test in order to correct the size of the test, that is not horrible, but is of course is a little bit oversized in small samples. We also carry out power simulations, and we see that even with very tiny, small correlation, different correlation between the forecast and the target variable. Here, imagine the correlation is just, you can have a forecast with a correlation of 0.10, and the correlation 0.13.5. And we have like with 1,000 of observations, or a power of almost 60% at the 10% level, 45% at the 5% level. Well, the different correlation is almost 10%, it's less than 10%, 7.7%. We have almost perfect power for large samples, much lower power for small samples. And if the correlations are different, quite different, let's say 0.15 of differences, then we have, again, perfect power for large samples. Smaller samplers, smaller samples are decreasing power. So we also try multi-step ahead, and think we ran out of time.
Yeah, but we really, but we can after the session we don't have to leave, so we can continue with the presentation or discussion. But
okay, so can I say just a couple of conclusions here?
Yeah, but very quickly. I mean,
30 seconds.
Yeah.
So okay, thank you. So in summary, we find a paradox: mean square prediction error comparisons are not always consistent with correlations. So we develop a test with correlations between the target variable and forecast, and it behaves very well in our simulations. That's it.
Okay, thank you very much. Now I would like to pass word to Dr. Rahul Pathak, which we were talking about. Let's not.
Can you hear me? Okay. Let me share my screen here. And probably because we are short on time, I'll probably prefer to take questions at the end. Can you see the screen?
Yes.
Okay, great. Hi, my name is Rahul Pathak. I'm an assistant professor at the Baruch College at City University of New York. This is joint work with Dan William, who is, I think, on the call, and you can chat with him on the call. This is, in fact, a paper that probably after seeing the earlier two presentations, I think probably should have been in a COVID-related panel. It's a more applied paper and doesn't talk about estimators, etc. And we are looking at the comparative accuracy of COVID-19 forecast. This is still very preliminary work, so we would love to have any feedback that you might have. And we are focusing on the case of United States. US, as everyone knows, has been the epicenter of the pandemic since March and April. Right now, roughly around 8 million cases, 220,000 deaths. And in fact, in the last week or so, last couple of weeks, we are seeing another resurgence in the number of cases that probably will last for another 2-3 weeks for sure. And there are different models that are saying different things. But things are bad. In the area that where we live in New York and New Jersey, we were hit pretty early with the pandemic, and now we are seeing another resurgence in the last few weeks. And several organizations have been involved in the forecasting of COVID-19 trajectory, and there are organizations like CDC, which is Center for Disease Control and Prevention in the United States, that are in the business of putting together all these forecasts and creating some sort of an ensemble forecast. And of course, we have a problem of plenty when it comes to COVID-19 forecast. There are forecasts that are all over the place. People are forecasting different kind of variables, particularly the number of cases and number of deaths. Cases are probably much more all over the map. Deaths are relatively more accurate in the sense that the testing capacity and these kind of things don't affect deaths, the counting of deaths. There are a variety of models that are out there in the public domain, and there has been certain public mistrust of the COVID-19 projections that have been done. If you remember the Imperial College London forecast that came out on March 16, that predicted huge amount of deaths in US and UK. That of course didn't pan out the way it was proposed. Dr. Anthony Fauci, who has been the leading member of the COVID task force in the US, he at the end of March said that we don't need to make a projection when it's such a moving target and you could easily be wrong. Certainly something that probably members of this association don't agree with. And there are a variety of models that are out there. There are the epidemiological model, mechanistic models, the most popular one being the SEIR model. It stands for, I think, susceptible, infectious, responded, something, I'm missing the E there. And there are different versions of time series models. There are computer science departments that are employing different deep learning and machine learning techniques, etc., etc. And all these models, as I just showed in the picture on the last slide, are all over the place. There are different assumptions that are built into the models, and accuracy, of course, varies with the kind of assumptions that are used in these models. And the primary, one of the biggest assumption that is built into the models is the social distancing assumption, that what would be the aggregate level of social distancing in the coming weeks, which nobody easily is able to predict in some sense, because there are the seasonal effects and, of course, policy level handles that are influencing the numbers. The forecasts are available at different level of aggregation. There are forecast at the national level, forecast at the state level, at the county level, and there are variety of variables that are out there. So some folks are forecasting a number of cases, which often is wrong. There are forecasts on hospitalizations, a number of ventilators that would be needed, bed capacity, etc. In this paper, we primarily focus on the central tendency of mortality, because that we think probably is a little bit more robust and subject to less measurement error in some sense. And data availability has changed over time. One of the biggest problems that I think people who are in the business of forecast evaluation often see is that old forecasts disappear. So we have been downloading these forecasts since March and April. Some of the organizations have done a good job of archiving with GitHub, etc. But there are some forecasts that have simply disappeared into the ether. And the reporting formats of forecast changes, assumptions change, sometimes models change, and then there are random idiosyncratic things like forecasters take a break for a few weeks and the series is broken and things like that. Of course, we are not, as of now, because this is preliminary work, we are working with just standard mean error MAPE kind of measures, but going forward, we would probably like to explore some other estimators that are out there, and probably some folks on this panel can suggest something that would be more useful in capturing the differences. Now, we compared basically two sets of models. There are two models that are from Columbia University, Mailman Institute of Public Health, and Institute of Health Metrics and Evaluation at University of Washington. And in these two models, we use the data from the first phase of the pandemic from March to May. And partly this is because these two models were in the center of public attention. IHME was being used by White House. Columbia model was being advertised in the media and probably also led to some behavioral changes in the way public responded, and partly because of data availability issue. And in the second series, we compare models from University of Texas, Austin and Los Alamos National Laboratory, and these numbers are available at the state level, and we covered the period from April to mid-October, that is last week, last couple of weeks. Models are selected on the basis of variation and differences in methodology, the different regional location of the forecasters. Some of them are on the East Coast, some of them are on the West Coast, data availability, of course, and all the forecasts we compared to the accuracy, the actuals from Johns Hopkins repository that some of you might have heard of by now. Now, there is significant variation in the models. The Columbia University model and UT Austin model is different variation of SEIR model, which is the epidemiological mechanistic model. UT Austin embarked on this model a little bit late. In the initial month, they were using more curve fitting sort of approaches. And IHME and LANL is mostly a statistical curve fitting sort of approach, but IHME included also the transmission a little bit later, but they discontinued the series. I won't go into the details of these, but the idea is that Columbia and UT Austin are what we'll say are heavy on the epidemiological components, and IHME and LANL are heavy on the statistical components. So just to kind of show you a visual picture of IHME forecast, which was the forecast that has been criticized a lot because it underestimated in some sense the mortality, and which was true certainly in April, etc. So these are the first forecast they made, the last forecast they made, the average of the forecast, which is perhaps the most important one, a weighted average, and the actuals are the mortality estimates from Johns Hopkins. And we see that in the early phase of the pandemic, uh, it was quite an effective model in some sense, but it certainly missed out on the resurgence that happened towards the end of June and July, and they didn't anticipate any of that in
But
their
can I ask a question
projection.
here?
Yeah.
So when you're showing this forecast, are these what kind of horizons are they forecasting for? So is one step ahead, one day ahead? So these curves that you're
So
plotting here.
Yeah, Pablo, I'll come to that in just a moment. So
Okay.
so here in an average, so they are forecasting for every day, and sometimes we take an average of every day. So average is there might be 5 forecasts for 3, like a particular date of 28th May. So we take an average of that. Okay.
So, but what is
And
the
I'll come.
horizon they're forecasting? Is one day ahead or 1
So
week
they are
ahead?
forecasting. So they are forecasting multiple weeks ahead.
Multiple
Sometimes
weeks.
even sometimes even months, 1 or 2 months ahead.
Okay.
So that was the IHME story, which I mentioned didn't capture the resurgence that happened in June and July. But if you look at the Columbia forecast, it was little bit off the charts, or quite substantially off the chart, which was similar story to Imperial College London in some sense. But they did capture the resurgence that happened towards the end of June and July. And if you want to look at this picture without that distorting first projection, the story does relatively hold true, and they were somewhat close in some sense. But if you look at the aggregate error measures, they certainly don't outperform the IHME forecast. If you look at just the average of the forecast or the absolute errors, IHME does overperform the Columbia forecast in some sense, but IHME also underestimates mortality, and that has been one of the criticisms of the IHME forecast, and something that makes it probably attractive to some of the politicians and policymakers in some sense. Now, the other set of forecasts was from the Los Alamos National Laboratory, and I'm just reporting the averages here. And we again see that similar story in the first phase of the pandemic. They were quite off the chart, but things have got better over the course of the summer and the fall last couple of months. And if you look at the UT Austin model, we again see a similar story. They were like the Columbia model, they were predicting quite a huge resurgence towards the end of May, which didn't turn out to be true, but they have stabilized in some sense over the subsequent months. They discontinued their forecasts for certain weeks in August and September, so we don't have data available during this period, but they do have numbers for last few weeks, and it does appear that their forecasts have caught up with the reality in some sense in the last few weeks, and it looks pretty good overlap in some sense. And that raises the question that have these forecasts got better over time? Have they improved over time as the pandemic has progressed, as the understanding of the disease has got better, as the models have become more refined in some sense? So in this figure, we just break these numbers down by the period of the forecast when the forecasts were done. So these are the forecasts that were done in April and May. These are the forecasts that were done in June and July, and these are the forecasts from August onwards. And certainly for the LANL model, we see that certainly April and May, they were not doing the appropriate forecast. Things got better over summer, but from August onwards, the forecast is pretty sort of good in some sense. And I'll show you the numbers in just a moment. And if you look at the UT Austin model, certainly we see a similar sort of a story. We see that the summer was pretty good in terms of the predictions that UT Austin model did. And because some of the structural breaks here, the picture is a little bit distorted for August till now. And if you look at the aggregate numbers, we do find on an average, and now average here comes with a huge disclaimer related to all these periods and how we bin them, etc., and the problems that are associated to averaging in first place. But LANL model does have lower absolute errors over the entire period of the forecast, but not so much if we break this down into different periods in some sense. LANL overestimates mortality rather than IHME was underestimating mortality in some sense. So it does appear on a very surface level that LANL outperforms the UT Austin forecast. And which brings us to there was one more thing which people are interested in, and that probably relates to Pablo's question in some sense, is the forecast length. So these forecasts are pretty effective in some sense for 2 weeks or so. They do a good job, but after 2 weeks, things start to go a little bit crazy in some sense, particularly for UT Austin. We do see that the errors increase significantly after a period of 2 weeks. So overall, the key questions here in some sense are which models are relatively doing better, and there is no sort of a policy. There are certain policy implications, but we are not doing a judgment on the processes of these organizations. IHME model does underestimates mortality, but does outperform Columbia model, and LANL model also outperforms the UT Austin model. So on the surface, it appears that the models that rely on more statistical approaches, at least in the short term, are outperforming the epidemiological models, which are going a little bit awry in some sense. But there are a lot of issues related to the assumptions that are built into the models that are there, related to social distancing, related to some of the gaps in the data, related to the nature of the disease and what is the information about immunity levels, etc. So we are not arguing that time series models or these curve fitting approaches outperform it, but probably for short-term policy decisions like imposing a lockdown, etc., these probably tend to be more reliable than the epidemiological models that are certainly needed to explain long-term transmission of the disease. You can't use the statistical time series models to kind of project the nature of the disease 6 months out into the population, because you need certain population characteristics, disease characteristics, etc. These models have improved over time, but we are anticipating changes in social distancing, changing in the policy sort of interventions in terms of reopening, etc., and probably medical developments. Who knows, probably 3 months from now, we might be in a better situation, fingers crossed. So we would like for these forecasts to go wrong if there are certain medical improvements that happen. So going forward, there's a lot of work ahead for us. We want to update these numbers for the second wave of the pandemic and compare these models concurrently. Right now, we are doing this in 2 separate bundles in some sense because of the data availability and comparability issues. But going forward, we'll try to kind of probably add some more forecasters, couple of more forecasters, depending on their regional location, and also look at comparing all these indicators simultaneously. Another sort of an thing to do for the coming weeks is looking at the state level numbers, and we do see a significant state level variation in the data. So for example, New York and New Jersey, we see significant overestimation, partly because of the fact that New York and New Jersey were hit early, but we do see certain biases even now in some sense. So these are numbers for what will the pandemic look like by different forecasters in the coming weeks. And we see that for states like Wisconsin and Colorado, the spread between forecasters is quite huge. But if you look at a state like Washington that was hit early in the pandemic, we don't see that level of variation. location. And there might be different regional factors, different policy and political factors, forecaster location related factors, and we want to look at these issues in a more systematic way going forward. Another issue to kind of take into account, and we'll probably love to hear any ideas if there are any on how to adjust for social distancing assumptions and actuals. So folks have used things like cellular mobility, etc., as a proxy for social distancing. So probably there is a way to kind of adjust for that, or probably we don't need to adjust for that. This is something that forecasters should have done. And alternative or error measures. These measures that we are using are relatively more straightforward, more simple. But if there are other measures that will probably capture this in a better way, we'll probably like to hear about that. So I am just 1 minute short of my time. I'll stop there, but I'd love to hear any feedback through email, or you can follow up on the app in the days to come. Thank you.
And thank you. Can I have one? First, let me say that we don't have to end the session. We can discuss it. There's no problem in that. The session does not have to end at the whatever time is in your region. Can I have one question regarding the presentation?
Yeah.
So in the slide where you separated the data into 3 parts in the time segments, it seemed to me that none of the forecast accounted for any kind of seasonality, that there is very strong seasonality in the data, and none of the forecasts seems to be capturing that. Is that the desired thing, or is there some reason for that?
Yeah, so seasonality certainly, as it comes to COVID, is an issue, but we just have 6 months of data, right? So how do we kind of, if we have multiple years of data or something, we can capture seasonality a little bit better. And certainly, yes, summer seasonality plays a role in being able to predict the pandemic in a better way during the summer.
Yeah, I meant seasonality by the days of the week, because that seems to be the pattern that during the weekend there's little.
Oh, okay. So yeah, so I have a moving averages in the 7-day moving average in the paper, but we updated the numbers, so I didn't include that on the slide, but I can certainly have. So 7-day moving average would be better than daily. So we do see those fluctuations on weekends. So probably we should report 7-day moving averages rather than the daily estimates.
And the comparison was made against the individual day data or the moving averages?
So all of this is compared. So we are not using moving averages as of now,
okay.
but probably going forward we need to use moving averages. And the thing is that the death data is also available every day. So it was also related to the daily the compatibility between different data sources.
Oh, thank you.
I'd like to add here at this moment, there's a difficulty with the epidemiology models, and we haven't really resolved it. Maybe someone in the room knows the answer. There are forecasts across a large range of percentile possibilities, and we're making assumptions about what counts as the midpoint of those forecasts, evaluating across all different from 5 percentile to 95 percentile ranges is impossible. So we actually made one assumption early on, which we used with comparing IMHE and Colombia, and a different assumption when we evaluated the more recent data. And the first data set, we assumed the 50th percentile was intended to be the midpoint of the forecast. And the more recent, we've seen public discussion of the 90th percentile, so we're treating that as the midpoint of the forecast. But we really don't know, and are not finding it easy to determine what the midpoint of the forecast is. So if anyone in the room knows the answer to that question, we would very much appreciate an email message back to one of us.
You know, I have a question here because I'm very impressed. We're writing a paper here about COVID, but about infections, not daily deaths, and for a number of countries here. And if you see the curves of the daily infections or even death, you see that they are very smooth. They're non-stationary, but they're smooth. If you compare with financial data that is really hard to forecast, you would think that, well, forecasting this smooth series should be much easier. But then you see these huge forecast errors, and that's something really difficult to understand from an intuitive point of view. I mean, people is struggling with the financial forecast, but you see the series seems like a random walk, and stochastic trends everywhere, so they look difficult. But this series don't look that difficult. Yet the forecast that we have been receiving out of these institutions seems to be really poor. So you have an intuitive explanation why this is happening?
I think Pablo, on that, probably aggregating data across countries, like if you look at the US data, that might be very much different from, say, I've been working a little bit on Ghana in India, like there the Ministry of Health decides how many cases are there that day. So whatever data they get from testing laboratories, they modify that because of the political reasons. So they are making it smooth in some sense. Probably in US, there is a little bit more transparency. So breaking it down by different countries, probably you will see a decent amount of variation in the data.
And have you tried phenomenological models that are like simpler benchmarks to which one would expect these more complex models these models should outperform the phenomenological models, logistic models, something like that, to use some like a benchmark?
Yeah, so that's something on the cards, and Dan can add to it. But like right now, we are just aggregating the data, and we just downloaded the data until a couple of weeks back. So we have to constantly update the data. So we're still working with simple error measures, but that's something on the cards, and Dan can add to it.
So there's really no history. Well, there's history now, but there was no history when these data started back in March. Without history, simple models, just even the simplest models, I've written about a lot of simple models, and it just there's nothing to build a simple model from. We could be running simple models, say, from maybe start of June or something like that, but there's far too little historical data, especially with a very large weekly seasonal effect. It would be it would seem to be unreliable to do that, if that makes sense. One thing, we could fairly easily go back and deseasonalize the data. In other words, just calculate the weekly moving average. Some people use 1 weekly moving average, some people use 2 weekly moving average, but calculate the weekly moving average and calculate the errors from that rather than from the actuals each week, and it may show a different story. Although when the epidemiology models are completely in excess of the even the highest moment in the weekly period, I don't think it's going to have a big effect on the errors, except the averaging effect. So I'm not sure what will result in showing better forecasts. There's also a question of whether the same data are reported every day, right? In the United States, there are 50 states, and there is evidence that different states report different kinds of data. So that also undermines the idea that we're getting meaningful data to even think about a forecast. I mean, it's the data reported, so in a sense, it's the forecast of the data reported. but there is a separate series, at least in the United States, of excess deaths. And a lot of people think the excess deaths almost entirely relate to COVID-19. And so the errors might actually be better estimated off of the excess deaths rather than if you see what I'm saying. It's just really hard to be sure what we should be doing.
Well, but I think that the idea of using these simple phenomenological models is to see, it's not because of this model could be doing a great job, but this would give us the idea if these institutions are doing a better job than these simple models. That was something interesting to say. You have huge institutions using different, collecting data from, cell phones, mobility, probably excess deaths, now that you're saying that. So that they have plenty of information. I would say plenty, but some information, some additional information that, of course, the simplest models don't have. So it would be interesting to know if, with this additional information, that they are able to outperform the simplest models. Maybe they don't, so that would be a huge result. But if they are, well, there's something a little bit good, I guess.
Thank you for the feedback.
All right.
Sure. Thank you, everyone.
Thank you all for coming and participating.
Take care. Good night. Good morning. Whatever.
Good luck with the paper.